All right, welcome to day 2 of our review of Unit 1 from last year. If you could have your warm-up out, we're going to do that together. In your planners, you can be writing day 2. So what we've got pictured here in the warm-up, this is called a piecewise function. You should have seen them last year. We're going to work with piecewise functions some today. That's why we're looking at it in the warm-up. And what this is it's two different equations depending on your values of x. So what this is meaning is if x is greater than or equal to -2, then we're going to sub into 2x plus 2. But if x is less than -2, we're going to sub into -3x plus 1. So it's different equations depending on our values of x. So you can stick that warm-up sheet away. We'll go over to your homework from day 1. First one, equation of a line passing through a point. So we got to do y minus y over x minus x. We eventually get 5, 6. So we'll take that y equals 5, 6x plus b and sub in one of our points. Doesn't matter which one. Multiply to get 25, 6. I subbed in the 5, 2, by the way. Subtract over, and you get the b is -13, 6. To finish off, fill in for your m and for your b. Make sure you've got regular x and y in your equation. Number 2, that open circle, we're just working right to left. So -11 is going to go into the g equation. -11 plus 5 gives us -6. So now we'll do f of -6. That goes into the f equation. 2 over -6 gives us -1/3. Okay, don't round or anything if it doesn't tell you to round. Just keep it in fraction form. G of f of 4, we're going to put 4 into the f function. So 2 over 4 gives you a half. Then put that into the g function. So you get a half plus 5. You can either say 5.5 or 11 halves is fine as well. And then for our algebraic rules, f of g of x, we'll put g of x where x is in f's equation, so 2 over x plus 5. And then going the reverse, we'll put 2 over x in g's equation, so 2 over x plus 5. And down on the bottom, do your graph, then do Control T to get some points. Remember, we always do our stuff is greater than or equal to 0. So for domain, we'd have x plus 2 greater than or equal to 0. Subtract the 2 over. That's where we get our domain from. Smallest y is 0, and it goes up forever. So we have y greater than or equal to 0. Now, for your other one, you probably had to extend, do one of two things. Either extend the grid sum or make sure to put your x-axis kind of high so everything can fit. All real numbers should be our domain, and our smallest y was -17, and it goes up forever, so we have y greater than or equal to -17 for the range. All right, if you could flip over to the next page, page 8, we're going to start by looking at inverses, and make sure to have your calculators out as well. We'll be using those a decent amount today. So when two functions are inverses, it means if xy is on the graph of one, yx would be on the graph of the other. So the points are flipped, and that's true of all the points. Graphically, what happens is it's reflected over the line y equals x. So if the x's and y's are just getting switched, we can use that feature to help find the inverse equation. So first, let's think of f of x as y. So let's write this as y equals 2x minus 5. So we're going to switch where x and y are. So this is x is 2y minus 5. Then all we do is we work to get y by itself. We'll add the 5 over to get x plus 5 equals 2y. And we'll divide by 2. And you can either divide everything by 2 or put it all over 2. So this would be, we could write it as 1/2 x plus 5/2 equals y. If you wanted, you could have left it as x plus 5 over 2 equals y. That's fine also. But that is what our inverse would be. Now, let's talk about that notation there. The f with the little -1, that's read as f inverse of x. So we use that little -1 just as a notation. It doesn't mean like move it to the denominator because it's a negative exponent. You see that most frequently if you hit the trig button on your calculator. That second row has sine inverse, cos inverse, tan inverse. So that's one of the most common spots that you see it. So we're going to do a few more inverse ones. So originally this is really y equals square root of x plus 4 over 3. So to do the inverse, we'll change the x and y. So x equals square root of y plus 4 over 3. Now we just need to work to get y by itself. We can put the x over 1 and cross multiply. And I'm going to move that up here. We'll have 3x equals square root of y plus 4. We're going to square both sides. When we square the left, we got to make sure to square everything. So 3x times 3x is 9x squared. And we'll just have y plus 4 over on the right. We can subtract the 4 over, and we get 9x squared minus 4 is equal to y. So to finish it off, our notation, f inverse of x, would just equal 9x squared minus 4. Moving down to the bottom, we want to find our inverse. So let's rewrite the f of x as y in the original equation. As soon as you see find the inverse, we want to think switch the x and the y. So let's move the x where the y is, move the y where the x is. And notice it's physically only the x and y. Any exponents, coefficients, those all stay put. Now let's just work to get y by itself. We'll start by subtracting the 7. So we'll have x minus 7 equals 2y cubed. We can now divide by 2. And you can divide them each by 2 or just do it all over 2. Just to switch it up a little from the other one we did, let's leave this one all over 2. So I have x minus 7 over 2 is equal to y cubed. Now to undo a cubed, well, to undo a squared, we do a square root. So to undo a cubed, we should do a cubed root. For the cubed root, you just put the 3 in the little crevice there. So we'll have cubed root of x minus 7 over 2 is equal to y. And then the last step, they didn't give us a blank for it on this one, but just put it back in our inverse notation. F inverse of x is how we would read it. And it would be cubed root of x minus 7 over 2. Now just to drive home our inverse idea here, if we were to graph our original and our inverse and look at their tables, we would find all the coordinates would be flipped. So like in the original, we would have 1 comma 9. In our inverse, we would find we'd have 9 comma 1. In our original, we would have 2 comma 23. In our inverse, we would see we'd have 23 comma 2. So they'd all be flipped. So the last two inverse ones we're going to look at, notice we just have a slight difference in these equations. One of them has the plus a outside the cubed root, one of them has the plus a inside the cubed root. And I just want to show you how things turn out differently in those two scenarios. So let's start with the original as a y equals. To do the inverse, we switch the x and the y. And now work to get y by itself. We'll subtract the 8 over. We'll divide by 4. And then the opposite of cubed rooting something is cubing both sides. We've got to make sure we cube everything on the left. We don't have to actually multiply it out, but we'll have x minus 8 over 4 all cubed equals y. And then for the final step, just put it back in our inverse notation. This time we had h, so we'll have h inverse of x equals x minus 8 over 4 all cubed. So we can see the slight difference in the next one. We'll write it as y to start out. Switch where the x and y are. Oops. That should be a y. Now work to get the y by itself. So we'll start this time by dividing by 4. And we'll get x over 4 equals cubed root of y plus 8. We'll need to cube both sides. I'm going to move it up here. We'll have x over 4 cubed. Or you could write that as x cubed over 64, because that's what we'd get if we cubed them both, your choice. And then to get y by itself, we'll just subtract the 8 over. So we've got x over 4 cubed minus 8 equals y. To finish it off, we'll just put it in our inverse notation. H inverse of x is equal to x over 4 cubed minus 8. So notice that one slight difference in our original, whether the 8 was added inside the cubed root or outside, yielded slightly different results as well in our inverse. All right, now we're going to look at graphing some piecewise functions. In the tables there, first thing I want you to do is cross out that 1.1 and that 4.9. Just cross out those rows. We're not going to have them. So we've got a piecewise function here. Based on the warm-up, we know we should use the top one when x's are less than or equal to 1. We should use the bottom one when x is between 1 and 5. So how did I know to get these x values? Well, in that left-hand table, I picked 1, and then I just picked a few values that were less than it. Next to the 1 in the left-hand table, because we have x less than or equal to 1, I want us to draw a closed circle to remind us that that's closed. At our end values in our table, we'll always want to determine, should we have a closed circle, an open circle, or does it keep going on forever, so do we have to put an arrow? Well, because we have x is less than or equal to 1, we need smaller than 1. So that's why we have 0, -1, -2, -3, and so on. But we could have kept going if we wanted. So next to -3, I want you to put an arrow to remind yourself when we plot that point, we're going to want an arrow. Now going over to the other ones, we're going from 1 to 5. That's why we have 1, 2, 3, 4, 5. And because we're not equal to on either of those, we're going to have open circles. So stick open circles next to the 1 and the 5. Any of the other points in the middle, they're just normal, regular points. Just the ones at the ends in our table, those are the ones we have to spend a little bit of time thinking about. Well, from here, we're just going to go to the calculator. So let's go to a graphs page, and we're going to put in the top one, x plus 2. We'll do Control-T to go to the table. And we're concerned about 1 to -3. So those are the ones we want. So we'll just fill those things in our table. So we had that 1 was 3, 0 was 2, then we had 1, 0, -1. Going back to here, we can add a new graph by doing Control and Dock. Control Dock adds a new graph. It actually adds a new page, and you can add any type of page you want. Our other equation was -x. Hit Enter. Do Control-T to get your table. And we wanted from 1 to 5, -1, -2, -3, -4, -5. Now that one wasn't bad. You might have been able to just sub that one in by hand, because it's just negating the x values. So we're just going to plot these and make sure to have our things at the end. So I'm going to plot that 1, 3 first on the left. So we'll have a closed circle at 1, 3. Then all those intermediate points are just regular closed circle points. So we have 0, 2, we have negative 1, 1, negative 2, 0. And then at negative 3, negative 1, we want to end up putting an arrow to show it keeps going. And then we'll just connect those points. Now from the other one, we're going to have an open circle at 1, negative 1. Then all the intermediate points just get normal points, closed circles. So you have 2, negative 2, 3, negative 3, 4, negative 4, and then an open circle at 5, negative 5. So we'll connect those, and you just connect the outer edge of the open circle when you draw that in. And that would be our graph of this piecewise function. So if we go to the next one, we're going to take some of the training wheels off. The difference now is, one, we've got more parts, and also we've got to come up with the values for our table. So we're going to have 4 different t tables. So the first one we'll do for the 4 minus x. Well, we want x is less than negative 2. So let's put negative 2 as the first value. Because it's just less than, we need to put an open circle next to it. We want less than negative 2, so pick a few values that are less than negative 2. Negative 3, negative 4, negative 5. We could have kept going, so let's draw an arrow there to remind us that we need to put an arrow when we plot that point at negative 5. Our next one, we'll do a t-table for x squared plus 2. That one was just going negative 2 to 2. So negative 2, negative 1, 0, 1, and 2. Negative 2 was less than or equal to, so we need a closed circle on that one. The 2 did not have the equal to, so we'll need an open circle on that one. And we'll come back to those to find the table values. The next one, well, it's just always negative 3, and it's only when x equals 2. So we'll just have 2, negative 3. That's just going to be a point. And then the last one, we want greater than 2. So start with 2. It didn't have an equal to, so we need an open circle. Some things bigger than 2 are 3, 4, 5. We could have kept going, so we can put an arrow. And then for this one, we can probably fill that one right in and not even have to do the graphs page because it's just always 6. So all of these are just going to be 6. So let's maybe put the 4 minus x in a graphs page first. So remember, to get a new page, do Control and then Doc. We'll go to a graphs page, and we'll put in our 4 minus x. To get to the table, we'll do Control T. And we had negative 2 through negative 5. So there's those ones there. We'll have to fill in 6 for negative 2, 7 for negative 3, 8, and 9. So then x squared plus 2, we'll add a new graphs page by doing Control Doc to get a new page. Add the graphs page. We'll put in x squared plus 2. We'll do Control T to get the table. And we were going negative 2 to 2. So we got 6, 3, 2, 3, 6. Well, now we've got all of our points to plot. So negative 2, 6 is an open circle. Then the intermediate ones, remember, are just normal points. So you got negative 3, 7, negative 4, 8, negative 5, 9. We want an arrow. And we know to put the arrow going that way because that's where it would have carried on, connect to the edge of the open circle. Negative 2, 6, we have a closed circle. Well, notice that's just going to fill in that open circle. So we can fill that in with a closed. We'll have negative 1, 3, 0, 2, 1, 3, and 2, 6. Oops, 2, 6 was an open. Now that's a parabola, so we should draw it in with a nice smooth curve, not a pointed V at all. Next one was just a point at 2, negative 3. And then for the last one, we start with an open circle at 2, 6, which we already have. Then regular points at 3, 6, 4, 6, 5, 6. We'll put an arrow. Draw in your line. So the last thing we're going to look at today will be over several questions, but we're going to look at modeling from equations and then answering some follow-up questions from it. So down on the bottom of page 10, we're going to have f of x represent an arrow that's being shot through the air, and g of x is a bird that's in flight. So we're going to graph these both on the same graphs page. So let's do Control Doc and add a new graphs page. We'll put the f of x one in first. We've got negative 16x squared plus 60x plus 5. Well, there's two ways to graph another thing right on this page. We can either do tab or Control G as in graph. Tab's only one button, so I'm going to do tab. We'll put in the 5x plus 20 and hit enter. And we want a window that is going to show us everything. Now, I strongly suggest don't use zoom in, zoom out, because that can give you a distorted graph. Here's what I would suggest to do. Do a Control T and look at your table, and just scroll through and see what do some of those y values look like. So we've got a downward facing parabola, the green one. The highest I see is about 61. So let's make sure we can see up to at least 61. To get rid of the table, you just hit Control T again, and that takes the table away. So let's double click on our y value maximum. We want to be bigger than 61. Always be generous in case it goes higher, so I'm going to put 100 in. That'll make sure we can definitely see y equals 61. And notice now we can see our graph pretty nicely. So if we move over to page 11 now, while having that on our graph, we want to know what's an appropriate domain for this function. Well, x is representing time in seconds after the arrow's been shot, and the y's are the height of the bird and the arrow. Well, time can't be negative, so for our domain, we would just want to have x is greater than or equal to 0. Now for our range, it didn't ask for range, but let's at least talk about it. For range, the arrow's not going to keep going once it hits the ground. So really our range would just be from y equals 0 to whatever that highest y value is. But they didn't ask us for that in this case. All right, down on the bottom, we want to find our points of intersection. So to find points of intersection on a graph, you go Menu. Analyze Graph is where almost everything you'll ever need is in the graphs page. And we want to find intersection. Well, it asks us for the lower bound. So you have to move your cursor left of the intersection you want to find. I'm going to find that left-hand one first, so I'm going to move my lower bound over to there. Then it asks for upper bound. So you have to move somewhere to the right of the intersection you're looking for. So I'm going to move mine there, and then notice then it gives me the intersection. So this did not tell us where to round to. At least I don't believe it did. It did not. Let's go to 3 places, we'll say. So if you round that to 3 places, the first one we should have, 0.299. Comma 21.493. And the second one, and just a little pointer, a couple things. One, if you ever have to move a label, just hold down on it until it pinches it. Oops, didn't want to do that. So if you ever want to move a label, just hover over it till you get the hand, hold down till it pinches. I don't know if it'll let me do it on the computer one. And then you move it over. Another feature, if you ever want to see more X values, just click the X value, and by see more I mean more decimal places. Hit, oops, didn't want to do that either. If you click the X value once and hit plus, I don't know if it'll work. Yeah, it's not going to work on the computer one, but on yours, if you click the X value once and hit plus, it'll show you more decimal places if you ever need it. So for other intersection, menu, analyze graph intersection, select something left of that intersection, select something right, and we get our other intersection point. And it didn't tell us where to round. We'll just say let's do 3 places. So 3.139, comma 35.694. Well, what's the meaning of these? Well, remember the x was seconds and y was the height of the arrow and the bird. Both their paths are the same height at those same times. So these are the locations where the bird and the arrow will meet. Now, presumably, if the arrow is going to strike the bird at that first intersection, then maybe that bird's going to fall from the sky there. But based on our paths, that's what that's representing. So for what values of x is f of x greater than g of x? Well, f of x was our parabola. G of x was our line. So the green one is greater in between our intersection points. So to represent that, we would say that x is greater than 0.299, because you tell that in terms of x values, but less than 3.139. And what this is in the context of the problem, f of x was the arrow, so it is when the arrow is above the bird. In the next one, we're not going to state one value, but we're just going to talk about the meaning of this. If f of x minus g of x is equaling 6, that means f of x is 6 more than g of x. Well, f of x was the height of the arrow, and g of x was the bird. So basically what this would be telling us is when the arrow is 6 feet above the bird. So we're going to keep working with this same graph. Let's go over to the next page, to page 12. We're going to use our analyze graph to find the maximum point. So let's go menu, analyze graph, maximum. And we're going to be doing this for the f of x, the parabola there. First, we have to tell it which graph. So click on the parabola. It'll then ask for the lower bound. So we need to move our cursor somewhere to the left of the vertex, that turning point. And then upper bound, move your cursor somewhere to the right. It will tell us what that maximum value is. So we end up getting the point 1.875, comma 61.25. Well, what's the meaning of this? This means that at 1.875 seconds, the arrow is at a max height of 61.25 feet. Our next one, what values of x does f of x increase? Well, if we look at our graph, it's increasing, or in other words, having a positive slope all the way to that turning point. Remember, our scenario didn't start till x equals 0. So we would say 0 less than or equal to x is less than 1.875. Because x equals 0, our scenario starts, okay, and the height's immediately increasing. But then at 1.875, that's when it stops increasing and turns back around. When it decreases, it would just be the reverse. We would go from 1.875, and the x's would go till when it hits the ground. So 3.832. And actually, as I'm writing that, I realize we haven't found that 3.832 yet. So actually, if we go over here, if we want to find where it hits the ground, we want to see where that parabola comes back to the x-axis. So we'll want to do menu, analyze graph, and 0 this time. Select the graph we want, the parabola. Select something left of the 0 and right of the 0, and it tells us what the 0 is, that 3.832 to 3 decimal places. So that's where that number is coming from. And then the next question is kind of silly because we had to just find that. When does the arrow hit the ground? At 3.832 seconds. So last one for this video, we're going to find the average rate of change from 1 to 3 for f of x. So we're going to have 1 comma something and 3 comma something. When average rate of change is in a problem, you want to think slope. There's almost always one of these on the regents. So remember f of x, that's our parabola. Let's go over here and go to our table by doing a control T. Notice 1 is at 49 and 3 is at 41. So we'll have 149 and 341. And let's calculate our slope. We'll have y minus y over, if we started with the 49, we got to start with the 1, minus the other x. This will be 8 over negative 2, so in other words, negative 4. A rate of change should be something per something, and it should be our y units per our x units. So we're going to have feet per second in this case, because our y units was feet and our x unit was seconds. And the meaning of this is, on average, the arrow dropped 4 feet per second on this interval. That's it for this video. You got your day 2 homework to be doing for next class. Have a great rest of your day.